Hello everyone. Welcome to the 8th lecture on partial differentiation. In this lecture, we'll discuss about Taylor series expansion of functions of two variables. Before proceeding to the Taylor series expansion of functions of two variables, let us recall what is Taylor series expansion for function of single variable. Let fx be a function of single variable. Then we know from Taylor's theorem of functions of single variable that Taylor series expansion of fa plus h is fa plus h f dash a plus h square divided by factorial to f double dash a plus up to like this h raised to the power of n divided by factorial n nth derivative of f at a. Here this f dash a is the first derivative of the function f at the point a. F double dash is second order derivative of f at the point A. Similarly, f n a is the notation used for nth derivative of f at the point A. So this is the Taylor series expansion of a function of single variable. Let us proceed to the Taylor series expansion of a function of two variables. Let fxy is a function of x and y which possesses partial derivatives up to nth order and which is continuous in all points xy around a point AB, where this x lies in between a and a plus h and y lies in between b and b plus k. Then f a plus h b plus k is f a b plus h del by del x plus k del by del y of f plus 1 by factorial to h del by del x plus k del by del y square f plus 1 by factorial 3 h del by del x plus k del by del y whole cube of f like this. This is the Taylor series expansion of a function of two variables. Let us prove this. Here fxy is a function of two variables x and y. Now by assuming y as a constant, this f of xy can be seen as a function of one variable x. If we assume here we have a function of two variables x and y. If you assume y as a constant, then this function f of xy can be seen as a function of single variable of x. So by Taylor series expansion of functions of single variable, we have f x plus h y plus k is equal to f x y plus k, because here we are assuming y is a constant. So y plus k is not changing here. F of x plus h y plus k can be written as f x y plus k plus h del by del x f of x y plus k plus h square divided by factorial to del square divided by del x square f x y plus k like this. Because in the case of functions of single variable, we have seen that f x plus h can be written as f x plus h f dash x plus h square by factorial to f double dash x plus h cube divided by factorial 3 f triple dash x like this. So in that way we have assumed y plus y as a constant. So here we can see that y on the left hand side of the equality sign and on the right hand side of the equality sign is not changing. Here we have y plus k. Here in the first term after equality sign, we have seen that it is y plus k. In the second term as it is y plus k. In the third term it is also y plus k. So this y is not changing. Y plus k is on the left hand side of the equality sign as well as on the right hand side of the equality sign. Only here we have seen that the function is changing for values of x. So x is varying here. So we can say that this function of two variable is a function of single variable when we assume y as a constant and x is changing. So the expansion of f x plus h y plus k can be written in this way. Let us denote this as equation 1. Now let us take x as a constant and change y. By taking x as a constant and expanding for y, we have f of x y plus k can be written as fxy plus k del by del y of fxy plus k square divided by factorial to del square divided by del y square f of xy. plus like this. Here we can see that this x is constant. It is not changing. Here on the left hand side of the equality sign, it is x. Here on the right hand side of the equality sign, it is x. Here it is also x. In the third term, you can see that here it is also x. But y is varying here. On the left hand side, here it is y plus k. On the right hand side, it is written as y. So this is also we have treated as a function of single variable in this case also by taking x as a constant and expanding fxy for y. Let us denote this expansion as equation number 2. Now we have two equations, equation 1 and equation 2. Now replacing equation 1 fx y plus k by equation 2. Here we have fx y plus k, here we have fx y plus k, here we have fx y plus k in equation 1. We can replace this fx y plus k by equation 2 because in equation 2 we have fx y plus k as f of xy plus k del by del y f of xy plus k square divided by factorial 2 del square divided by del y square fxy. Now by replacing this, we have fx plus h y plus k is this. The terms inside the first bracket is our first term of equation 1 after equality sign. This fx plus fx y plus k is written here in the bracket. Similarly, the second term is h del by del x. Here we have h del by del x in the equation 1 into f of x y plus k. So we have replaced f x y plus k by equation 2. So we have this inside the second bracket. Similarly, in the third term, we have replaced f x y plus k. So we have with us this expression for f of x plus h y plus k. Now let us simplify this. We have written the first term as it is. In the second term, we have operated the partial derivative del by del x inside the bracket. So in the first term of the second bracket, we have del by del x of fxy. Here it is del by del x of fxy. Similarly, operating del by del x on del by del y, we have k into del square divided by del x del y of fxy. We have operated del by del x on del square divided by del y square, which we are getting del cube divided by del x del y square f of xy. Similarly, in the third term, we have operated del square divided by del x square inside the bracket and we obtained this term, the third term. Now, we have this expression with us. Now, further simplifying this, we have taken f of xy as it is. Here h del by del x f of xy we have taken from the first term of the second line h into del by del x of f of xy. And from the second term of the first line we have taken k del by del x del by del y of fxy here, k del by del y of fxy here. For the second line we have taken the first term of the third line, h square divided by factorial 2 del square divided by del x square f of xy, and second term of the second line, k del square divided by del x del y f of xy, and the third term of the first line, k square divided by factorial 2 del square divided by del y square f of xy. And we have taken 1 by factorial 2 common. So by taking 1 by factorial 2 common, here it remains as h square del square divided by del x square f of xy. Here it is written h square del square by del x square f of xy. Because we have taken 1 by factorial 2 common, from here if we take 1 by factorial 2 common, we have 2hk del square divided by del x del y f of xy. So here we have 2hk del square divided by del x del y f of xy. Similarly, taking 1 by factorial 2 common here in the third term of the first line, we have k square del square divided by del y square f of xy. Here it is k square del square divided by del y square f of xy. So we continue in this manner. Now we have with us f of xy plus, here the second term is h del by del x plus k del by del y of fxy plus 1 by factorial 2. This term can be seen as h del by del x plus k del by del y whole square f of xy. If we take f of xy common, then this term h square del square divided by del x square 2hk del square divided by del x del y plus k square del square divided by del y square is nothing but h del by del x plus k del by del y whole square. So we have this term. So finally we have fx plus h plus y plus k as f of xy plus h del by del x plus k del by del y of fxy plus 1 by factorial to h del by del x plus k del by del y whole square of fxy plus 1 by factorial 3 h del by del x plus k del by del y whole cube fxy. Like this it continues. So this is the Taylor series expansion of the function of two variables. So now we have this expansion with us. Now replacing this x and y by ab, we can write f of a plus h b plus k as fab plus h del by del x plus k del by del y of fab plus 1 by factorial to h del by del x plus k del by del y whole square f of ab, like this. Here we observed one thing, that in this expression f x plus h y plus k, it is represented in the power series of ascending powers of h and k. Because if we expand this, in this term we have power 1 of h and k. Similarly, in the second term we will have h square k square. In the third term we will have hq kq. So this expression is represented in a power series of ascending powers of h and k. The expression of f a plus h b plus k can be expressed in ascending powers of x minus a and y minus b just by replacing h and k, because here we have seen that f a plus h b plus k is nothing but is a power series expansion of powers of h and k. If we need a expression in the powers of x minus a and y minus a, we just have to replace this h by x minus a and k by y minus b. So by replacing h by x minus a, here we can see that this a plus h will become x. If we write h as x minus a get cancelled with each other, then we have only x with us. Similarly, by replacing this k by y minus b, b get cancelled, so we have only y with us. So f of xy is nothing but f of ab plus, since we have replaced h by x minus a, we have x minus a into del by del x plus y minus b into del by del y of f plus 1 by factorial to x minus a into del by del x plus y minus b into del by del y whole square of f, like this. So here we'll get a expression which is a power series expansion in the ascending powers of x minus a and y minus b. In other words, this fxy can be expressed in the form of a Taylor series about a point AB as this. Fxy can be written in this way. This is just a notational difference. In the place of del by del x, we have written fx. In the place of del by del y, we have written fy. So basically this fxab denotes the partial derivative of the function with respect to x at the point ab. Similarly, this fyab denotes partial derivative of the function f with respect to y at the point ab. So here the notations used for partial derivatives are fxab is partial derivative of f with respect to x at ab. Fxx is nothing but the second order partial derivative with respect to x. That means del square divided by del x square of FAB. Similarly, FYY is del square divided by del y square FAB. So these notations are used here, and the expression fxy can be expressed in this way. Here we have an example. Expand e raised to the power of x sin y in powers of x and y by taking a is equal to 0 and b is equal to 0. By Taylor series expansion, we have f a plus h b plus k as f of ab plus h del by del x plus k del by del y of f plus 1 by factorial 2 h del by del x plus k del by del y whole square of f, like this. To obtain an expansion in powers of xy, let us take h as x and k as y. Because in the previous slide we have seen that to get a expansion in the powers of x minus a and y minus b, we have to assume h as x minus a and k as y minus b. Because we have taken here a as 0 and b as 0, so x minus a, that means x minus 0, so h is x and y is k is y. If we replace this h and k by x and y, we have f of xy as f00 because our a, b are 0. So f00 plus x into del by del x plus y into del by del y of f of 00 plus 1 by factorial to x del by del x plus y del by del y whole square f00, like this. Let us denote this as equation 1. Now let us compute these partial derivatives del by del x of the function f at the point 0, 0. Now our function f of xy is e raised to the power of x sin y. So f00 is, if we replace this x and y by 0, 0, e raised to the power of 0 sin 0, that is e raised to the power of 0 is 1 and sin 0 is 0. So f00 is 0. Now taking the partial derivative of the function with respect to x, del by del x of fxy is del by del x of e raised to the power of x sin y. Here we are differentiating this e raised to the power of x sin y with respect to x. So we are treating y as a constant. So we have sin y as it is, and the derivative of e raised to the power of x is e raised to the power of x. So partial derivative of the function with respect to x is e raised to the power of x sin y. Now the partial derivative of f with respect to x at the point 0, 0 is 0, because if we replace x and y with 0 and 0, we have 0. Now the partial derivative of the function at with respect to y is del by del y of e raised to the power of x sin y. Here we are differentiating with respect to y, so x is treated as a constant, so e raised to the power of x is constant. It is taken as it is, e raised to the power of x, and the derivative of sin y is cos y. Now partial derivative of f with respect to y is e raised to the power of x cos y. Now partial derivative of this function with respect to y at the point 0, 0 is, if we replace x and y by 0, 0, e raised to the power of x is 1 and cos 1 is cos 0 is 1. So we have 1 here. Similarly, the second order partial derivative with respect to x, del square divided by del x square fxy is del by del x of f of xy, and del by del x of f of xy we have e raised to the power of x sin y. Now differentiating this with respect to x, we have e raised to the power of x sin y. Now at the point 0, 0, this second order derivative becomes 0, because by replacing x and y with 0, 0, we have 0. Now del square divided by del y square f of xy is del by del y of fxy. Now del by del y of fxy is e raised to the power of x cos y. So we have del by del y of e raised to the power of x of cos y. Now the partial derivative of e raised to the power of x cos y with respect to y is minus e raised to the power of x sin y, because e raised to the power of x is taken as it is because x is treated as a constant, and the derivative of cos y is minus sin y. Now at the point 0, 0, this partial derivative becomes 0 because by replacing x and y by 0, 0, we have 0. Similarly, del square divided by del x del y of f of xy is del by del x of del by del y of f of xy. Now del by del y of f of xy is e raised to the power of x cos y. Now we have del by del x of e raised to the power of x cos y. Now the derivative is e raised to the power of x cos y because here we are differentiating with respect to x. Cos y becomes constant. We have taken cos y as it is and derivative of e raised to the power of x is e raised to the power of x. And at the point 0, 0, this is 1 because replacing x and y with 0, 0, e raised to the power of 0 is 1 and cos of 0 is 1. So we have 1. Now we can put these partial derivatives in the formula to find out the expansion. So now our equation 1 f of xy is this. Now we have to replace f of 0, 0, del by del x of f 0, 0, del by del y f 0, 0, what we have seen in the previous slide. Now by replacing this f 0, 0 with 0, del by del x f 0, 0 with 0, and del by del y of f 0, 0 with 1, we have this expression with us, which is equal to y plus x plus y plus like this. This is the Taylor series expansion of the function f of xy in the powers of x and y. Let us take one more example. Expand the function f of xy as e raised to the power of 2x minus y about the point 0, 1 in Taylor series. Now here we have the function fxy is e raised to the power of 2x minus y. Taylor series expansion of the function about the point ab is f of xy is equal to f of ab plus x minus a into del by del x fab plus y minus b del by del y fab plus 1 by factorial to x minus a square del square divided by del x square f of ab plus 2 into x minus a y minus b del square divided by del x del y fab plus y minus b square del square divided by del y square fab like this. Here we have expanded that x minus a del by del x plus y minus b del by del y whole square. Similarly, here in the third term, we have expanded x minus a del by del x plus x minus b del by del y whole cube, which is x minus a cube del q divided by del x cube f of ab plus 3x minus a square y minus b del q divided by del x square del y f of ab plus 3 into x minus a y minus b square del cube divided by del x into del y square f of ab plus y minus b whole cube del cube divided by del y cube f of ab like this. So this is the formula for Taylor series expansion. Now let us compute this. Here we have the function fxy as e raised to the power of 2x minus y. So at the point 0, 1, we have f01 by replacing x by 0 and y by 1. We have e raised to the power of 0 minus 1, which is 1 upon e. Now partial derivative of the function with respect to x is 2e raised to the power of 2x minus y because the partial derivative of this function e raised to the power of 2x minus y with respect to x is e raised to the power of 2x minus y into derivative of 2x minus y. Y is a constant, so derivative of 2x is 2. So it is 2 e raised to the power of 2x minus y. At the point 0, 1, the partial derivative becomes 2 e raised to the power of x is replaced with 0 and y is replaced with 1. So 0 minus 1, which is e raised to the power of minus 1. So we have 2 divided by e. Similarly, del by del y of fxy is minus e raised to the power of 2x minus y because e raised to the power of 2x minus y is written as it is and the derivative of 2x minus y with respect to y is minus 1. So minus e raised to the power of 2x minus y. So at the point 0, 1, we have minus e raised to the power of minus 1, which is minus 1 by e. Similarly, del square divided by del x square f of xy is equal to 4 e raised to the power of 2x minus y. And at the point 0, 1, it is 4 divided by e. Del square divided by del x del y of f of xy is minus 2e e raised to the power of 2x minus y. That means we are differentiating del by del y of fxy with respect to x. Differentiating this minus e raised to the power of 2x minus y with respect to x is minus e raised to the power of 2x minus 2y, and the derivative of this 2x is 2, so we have minus 2 e raised to the power of 2x minus y. And at the point 0, 1, this becomes minus 2 e raised to the power of minus 1, which is minus 2 divided by e. Now del square divided by del y square f of xy is e raised to the power of 2x minus y, and at the point 0, 1, it is 1 divided by e. Now using the values of the partial derivative at the point 0, 1 in the Taylor series expansion, we have f of xy is equal to 1 divided by e, because f of 0, 1 is 1 divided by e, plus x minus a. Our a is 0, so plus x minus 0, and del by del x of fab at 0, 1 is 2 divided by e, plus y minus b, that is b is 1, so y minus 1, del by del y of f of ab, that is f of 0, 1 is minus 1 by e. So we have replaced all those partial derivatives. At the point 0, 1, we have this expression for f of xy. So which is equal to 1 by e plus 2x divided by e minus y divided by e plus 1 by e plus 1 by 2 into x square 4 by e plus 2x into y minus 1 into minus 2 by e plus y square plus 1 minus 2y into 1 by e plus like this, which is equal to 1 by e plus 2x divided by e minus this becomes y minus 1 divided by e plus, if we expand this inside the bracket, we have 2x square divided by e minus 2x into y minus 1 divided by e plus y minus 1 square divided by e plus like this. So this is the expression in the powers of x and y minus 1. So this is the Taylor series expansion of f of xy about the point 0, 1, or this is the expression which is in the powers of x minus 0 and y minus 1. Here x minus 0 power is 1, y minus 1 power is 1, x minus 0 power is 2, here x power is 1 and y minus 1 power is 1, here we have y minus 1 power is 2. So this is in the ascending powers of x minus 0 and y minus 1. This is all about Taylor series expansion of function of two variable. In the next lecture, we'll discuss about maxima minima.